Okay, this is a quick video to teach youth members of the team how to figure out the gear ratio they need in a transmission and how to choose belt pulley sizes to get the behavior they need from the parts on the robot that need to be spun by motors. So the main thing that we're concerned about right now with this particular one is the fact that the harvester has to pick up balls off the floor while the robot is driving forward. So if I had to draw a ball and a robot, I'm going to put the robot bumper here, and we have some wheels, and our robot's going to be cruising forward with some speed, velocity of a robot, a little R there, VR, and it's going to encounter balls on the floor with the edge of this roller, and it's going to have to suck them up. So this roller is spinning with some kind of angular velocity. We'll call that omega sub r for the robot, for the roller, not the robot. And that's going to correspond to some tangential velocity at the surface of the roller. And if you think about it, if this robot is careening at this ball at V sub robot, we'll call it. In order for the ball not to just bounce off when it gets there, this roller has to be not moving relative to the ball, the surface that it encounters the ball, which means that it has to be going backwards at the same speed that the robot is going forwards on this bottom edge, so that the bottom edge is standing still relative to the ground. Because otherwise, when we hit this thing, whatever speed by the way, whatever speed we roll the ball forward at, the center of the ball will move at half that speed, right? Because if we're moving the top and the bottom is stuck to the ground by friction, as the ball rolls around, the speed of the center of gravity of the ball moves at half the speed of the top of the ball. So that's important too, because as we encounter the ball, we need to actually have VT going faster than V robot in order that when the ball ends up in here, it actually starts to suck up in here versus us just rolling over it because of the friction at this point of the bumper, right? So rather than have the robot come up and roll over the balls, we need VT, tangential velocity of that roller, to encounter that ball at greater than the speed the robot's moving over the floor. All right, so that's our objective here. VT has to be greater than V robot, and the question is, how do we achieve that? Given what? What do we know? Given we know that the angular velocity of the motor is some limit that's known, at least at zero load, and that can be found from a poster that's on the wall in the shop that has all the standard motors, and it has their stall torques, and it has their maximum velocity at no load. And that's going to be known in RPMs, revolutions per minute. And you're going to really want to divide that by 60 and express it in revolutions per second. There's only 1/60th of a minute in 1 second. So RPM is going to equal RPS is going to equal RPM over 60. And so you need to get that for the 775 Pro. Made by Vex. That's the motor we're using. You can look that up online if you Google it too. So this is a given. We're given omega of the motor, and we're given some pulley sizes in number of teeth. And that's all we need to know. Oh, and we're going to have a gear ratio that we get to choose on our transmission. I'll explain that in a second. But this is the transmission gear ratio. And I'm going to say this is, T sub I, because there's a lot of different pulleys with different numbers of teeth. I means the index of any one of these. Now we're going to draw this from the top. Now we've established the objective and talk about how the rotational speed of the motor gets translated into the tangential velocity of the edge of the roller when it encounters the ball. Okay. So we have 3 rollers that are going to come in, and they are all going to have gear teeth on them, right? Pulley teeth, and some of them are going to have 2 sets of teeth, but they're all the same, right? So I'm just going to call that T sub R, which is the number of teeth on all the rollers, and it's the same for all 3 of the rollers. All right, and so the front roller, if this is the robot, these are the arms, right, of the harvester, and there's a box in here that's going to handle, whoops, the box is going to be actually here. It's going to handle the balls. You know, balls are going to go into this thing, and they're going to spit out the back. When they come in, this is going to guide them into that box, right? And we have to put the motor to drive these pulleys somewhere. Now, the way a standard 775 motor works, you have a certain motor body with a cap on the end, you know, the wires come off of it. And it goes into a Versa transmission, which can consist of 1 stage of gear ratio, 1 stage of an encoder. This is all modular parts that bolt together. And then it can come right out to a shaft, and on that shaft you can put a gear pulley, right? Or you can add more stages in here and make this thing longer. You can put, you know, 3, 4 gear stages to really gear it down. So you have a 4-to-1, so you have a 7-to-1, so you have a 10-to-1, so you have an overall gear ratio of 4 times 7, which is 28, times 10, which is 280. That's going to make the output spindle speed, and I'm going to call that omega S of the motor, right? It's going to equal the speed of the motor over the gear ratio, right? So if this is gearing down 280 to 1, then we need to divide the speed of the motor by 280 to get the speed of the spindle coming out of the transmission, right? Because of the way this goes together, there's not enough room to put the motor in here between the box and this side of the arm of the harvester. So that's why Vex makes a handy little device called a Versa 180 degree transmission. What it does is it orients the motor one way and the transmission the other way, and it turns it around. So your motor sits here. It directly drives a gear pulley with some teeth on it. I mean a belt pulley with some teeth on it. It's passing through a plate that has another shaft with another pulley with a different amount of teeth on it. So I'm going to call this TS for the shaft, and I call this TT for the number of teeth driving the transmission. And then the transmission stages come on here, and you can bolt on, you know, your 4-to-1, your 10-to-1, whatever, but you have some kind of gear ratio out there. And then out the end of that comes another spindle, and another belt pulley. And that belt pulley can then drive these things. So what we're going to do is there'll be a bracket that this all mounts on, right? That'll bolt into the side of this. So we'll have our motor here. It's going to drive a belt that drives another belt that comes back through our gear box that drives another belt, or another pulley rather. Not driving belts, we're driving pulleys. And this is going to mean that this pulley is going to drive that roller is going to drive that roller at the same speed because these have the same number of teeth, and that roller is going to drive this roller at the same speed because they have the same number of teeth. But what we have here is a number of teeth, which is the output of the transmission. I'll call that T0, TO here. And that's going to result in a rotational speed that's omega 0, and I'm going to call this rotational speed omega T, and this rotational speed omega, oh, it's M because it's the motor, right? There's a spindle, it's the same as the motor. We'll use S to be consistent. Okay, we're going to change this to S to be consistent. So now the question is, how do we choose R, which is the transmission stages we have? And by the way, in stock in the shop, we have some 4 to 1, some 7 to 1, and some 10 to 1 stages. So we have those to choose from, which means we can achieve 28 to 1. I have 4 to 7. We can achieve 4 to 1. We can achieve 7 to 1. We can achieve 28 to 1. We can achieve 10 to 1. Let me put that in the middle of the stack here, because we have some 10 to 1 stages. We can go 40 to 1 if we use a 4 and a 10. We can use 71 if we use a 7 and a 10. We actually have 2 10s, so we can go 100 to 1 if we want. And then we can jump right up to 280 to 1. We can even go to 400 to 1, or 700 to 1, or 2800 to 1. So we have a whole range of gear ratios R that we can choose from. Now let's figure out how to get from this requirement to what to pick for T output of that spindle and for the gear ratios R that need to be, how we're going to arrange whatever stages we have. Right, let me just check that we're still recording. Okay. So, I already showed you how the rotational speeds of these things were connected. Now, the tangential velocity is related to the rotational speed of something by the circumference. Okay, so each time the thing goes around, and say it's going around, 20 times per second or 50 times per second, if we multiply that by the circumference, which is pi d, the diameter of the wheel, right? Pi d is the time it takes to go around from here. It's the distance around from here to here. So if it goes around that distance, x number of times per second, then the tangential velocity is that distance times the number of times it's going around, right? So that tells us what this is in terms of omega r, the speed of the roller. Omega r, the speed of the rollers, right? Now we got to get what the speed of the rollers are in terms of the speed of the things that are driving the roller. So omega r is going to be related to, what's the one coming out of the transmission, omega out, by the ratio of the number of teeth here to the number of teeth here. And now, so the question is, which one's on top, T0 or TR? Well, if you think about it, in a situation where you have a little belt driving a big belt, right? Then let's say this is, I'm just going to call this omega 2 and omega 1 for the sake of argument here. And this is number of teeth 1 and number of teeth 2. And this is the number of teeth around the pulley, right, on some shaft. Then the speed of this is going to be slower than this one, because if this is smaller, then every time this goes around once, it doesn't turn this around the whole time. It turns around some fraction, right? So omega 2 is related to omega 1 by the ratio of the teeth on 1 over the teeth in 2. Does that make sense to you? If T1 is less than T2, this number is less than 1, and therefore omega 2 is less than omega 1, right? So this thing has to spin fast to make this thing spin not as fast. So, likewise, we can do this here. We can put TR down here, and we can put T out up here, right? TR relates to WR in the same way that T2 relates to W1, T1 relates to W1 the same way T out relates to omega out, okay? So, now we have that. I'm going to get rid of this here. Now we've got tangential velocity in terms of the speed of the rollers and the diameter of the roller wheel. This is known, this is unknown, but now we've got the speed of the roller wheel, the rotational velocity, in terms of the rotational velocity of the output of the transmission, and the number of teeth on this gear versus the number of teeth on this, right, or pulley. Now we need to relate the speed of the output of the transmission back to the speed of the input of the transmission. The speed of the output of the transmission is going to equal the speed of the input, which we called omega t for the input over r. If you think about that, if I'm going to reduce it with a gearing of 4 to 1, then the output speed is going to be 1/4, 1 over r, times the input speed, right? That's easy enough. And then we have to figure out what the speed of the input to the transmission is in terms of the spindle speed of the motor. And that's going to be related in the same way all this was by the number of teeth as an input of the transmission on this 180-degree deal here, where this didn't draw the belt, but this belt drives this thing to reverse that. And the number of teeth on the output spindle. These two numbers are available to us from the product page on Beck's Robotics. Look for the Versa 180-degree transmission. Those two numbers are given, they're available to us. The speed of the motor is given, it's available to us. So we know what the input to the transmission is. Then we get to choose R to find out what the output of the transmission is. And then we get to choose the number of teeth on this pulley to figure out how fast, with the number of teeth on these pulleys, the wheels will go. So if we put all these things in a sort of a computational chain, then we have the velocity that needs to be greater than the v robot, right? So v robot has to be less than this, right? So we may as well just put it right there. V robot has to be less than v sub t. Well, what's v sub t? We can replace that with omega r pi d. So what's omega r? We can replace omega r with omega naught t output over t r of the roller, number of teeth on the roller. What's omega 0? We can replace that with omega t over omega r, the input spindle speed of the transmission in revolutions per second, over the gear ratio of the transmission. What's omega t? Well, it's omega s, the spindle speed of the motor, times number of teeth on the spindle pulley over the number of teeth input to the transmission pulley. So now we have an equation that tells us everything we need to know. We get to choose R from our available options using our 4 to 1, 7 to 1, and pair of 10 to 1 transmission stages. I think we have a pair of 4 to 1s too, so we could actually do a 16 to 1 or 160 to 1. And we don't get to choose TS and TT. These are given because they're part of the transmission. We don't get to choose TR because we already made it. And I'll come back with the answer for what those have on them in a moment. And we get to choose T out, which is the size of the pulley that we're going to put on the output of the transmission. So we need to look up spindle speed of the motor for the VEX 775 Pro. We need to find a T0 and choose an R from some combination of these ratios that we can multiply together to make this number come out greater than the speed of the robot. And I'm going to suggest that the speed of the robot is probably about 15 feet per second. Don't forget to convert to inches and feet and revolutions per minute on the motor to revolutions per second here. And there will be a prize for the student who chooses for me which stages, chooses for the team, which stages of the transmission we need to use that we have in stock out of the 4 to 1, 7 to 1, and 10 to 1, whether it's 1, 2, or 3, and what size of number of teeth on a belt pulley for HTD belt pulley available from Andy Mark or Rev Robotics perhaps, or certainly Vex Robotics. And it has to be one that has a 1/2-inch hex shaft drive. So it will look like this. 1/2-inch hex. Need to pick the number of teeth. We need to pick which of our transmissions to make sure that this roller spins faster than the robot goes forward. All right.